Welcome back, everyone, to Exploring Quantum Physics. I'm Charles Clark, and today you're going to follow the bouncing ball. So just to remind you, we're working with special functions, and today, for this part, we're going to especially be involved with the Airy function. So I encourage you to make this reference available to you. Though everything I'll show you is self-contained, but this is a good source of additional information. It's also appropriate for me to remind you of the short course, crash course on mathematics, reference on the solution of Schrodinger equations, known Schrodinger equations, and access to a simple numerical integrator that runs on a spreadsheet. In the previous part, we started out and we treated the first of these three simple one-dimensional examples, and we're now going to this part look at the linear potential. And I think actually we will have a very brief discussion about the quadratic potential at the end. I think the linear potential does sort of is the best thing to focus on because it gives one a very good framework for comprehensive understanding of the solution of the one-dimensional Schrodinger equation. Now, in the previous part, we solved for this constant potential, and we found that we could transform the Schrodinger equation into a standard form. And the key point about that standard form, well, there were two variants of it, difference in signs, according to whether E was greater than or less than the constant V naught. But in both cases, we had identified two solutions. Now, I should have brought this point up in the previous part, but here's a really good tool for helping you to make decisions about choices of the alternative pairs of wave functions that you will always face in solving the Schrodinger equation. This is the so-called Wronskian. The Wronskian of two functions is given by f g prime, so g prime equals dg dx. And this is a very good comparison tool to aid your decision making. So in the inline quiz, I'm going to invite you to discover for yourself the key property of the Wronskian operator and why it's so useful. So I guess you can see that in these two cases, you can calculate the Wronskian of these two functions easily. That's plus or minus 1, depending upon how you do it. And here it's plus or minus 2, I guess, depending on how you do it. But perhaps if you think about it, you'll see that if you have divergent behavior in this case of one function, then you should be able to find another one that converges. Or maybe it's easier to say that if you have oscillatory behavior of one function in this region and you pick another one, then that's also a solution. It's also going to be oscillating in order to keep the Wronskian a constant. So that's the real importance is that these alternative pairs of solutions, the Wronskian must be constant. Now, the solution to the linear potential, Schrodinger equation for linear potential, has very nice properties. So I suppose that these are the Airy functions must be less familiar to everybody must be less familiar than the exponential or the trigonometric functions to everybody. But if this is your first exposure to them, let me point out that this case of linear potential gives us two universal solutions that combine both the oscillatory behavior of the trigonometric functions and the exponential converging or diverging or converging behavior of the exponential function. So there's basically there's kind of a universal function of each type that covers behavior in the allowed versus forbidden regions. And that is, if you have a linear potential, then eventually, depending on the choice of V1, eventually the potential eventually gets larger than the energy, or eventually gets smaller than the energy, either way around. So in this sense, the linear potential is a very, very nice tool for understanding the behavior of quantum mechanical wave functions. So again, in this case, there's a demarcation point. Well, of course, these are two particular choices of function, and you can find their definitions in this chapter. And they both oscillate when the argument is less than 0, and then the AI converges for rho greater than 0, and BI diverges. And these two have implementations in physical systems. The one we're going to look at in detail here is the quantum mechanical bouncing ball, but this second type of area function becomes important in modeling things like the scanning tunneling microscope. Now, the bouncing ball problem is, as you'll see, it's important from a technical or theoretical perspective in terms of learning how to solve the Schrodinger equation, but it actually is something that has been recently realized, a remarkable experiment of the bouncing of a neutron confined in a trap and bouncing off a mirror. And there's actually experiments that measured the quantum mechanical spectrum of the Earth subject to the neutron subject to the Earth's gravitational field. There have also been some implementations in ultra cold atom systems. So we're actually going to solve the problem with reference to parameters that are germane to this recent experimental realization. So here we're going to describe this amazing neutron experiment. The starting point is something from freshman physics. V is equal to mgh, or V is equal to mgx. So the potential energy of the neutron is given by this form, where x is the distance going vertically off the surface of the mirror. G, acceleration due to the Earth's gravity. We just take a nominal value, 9.8 meters per second squared. M, the mass of the neutron, about the same as the mass of the proton. Here's a nominal value. We're just going to use a rounded number value. And now here is the boundary condition for x equal to 0. So in other words, the wave function has to vanish at the surface of the mirror. That's an idealization. It's largely true. And then the wave function has to oscillate and reach a point of whatever the energy is. The wave function must die off eventually in order for the neutron to be localized and continue to bounce back and forth in the way that we expect. Now, in order to cast this equation into appropriate dimensional form, we're going to define, I've worked this problem out in advance, so we're going to define our dimensionless coordinate rho in terms of this transformation, and I'd like you to look at that in the in-video quiz. Right, well, I hope that you found that you could solve the quiz question using dimensional analysis only, because if you just look at E over mg, I mean that tells you that dimensional analysis of this expression tells you the answer there. Oh yeah, so in other words, this parameter alpha has to have the units of energy. I mean, since rho is dimensionless as well, you can see that that's quite clear. Now, In the next brief inline quiz, just take it a step further, and this has to do with the relationship between rho and x. So if you were to draw a rho axis, where does it go in this mirror? And for example, there's an important issue regarding what does rho equals 0 mean? What is the physical interpretation of the value of that particular dimensionless coordinate? So I hope it was obvious, or I hope it was easy for you to find that the value of rho equals 0 describes the classical turning point. That is, what I say, the place where the velocity changes sign. It represents the maximum distance. Represents the maximum distance, maximum value of x for which is attained in classical motion. So that means that the function that we want is ai because well, it attains its maximum a little bit before rho equals 0, but it's the one that dies off as rho gets large, as rho increases beyond into the positive region, which is the classically forbidden region. So we know that we must, of the two solutions that we're going to use, we must use ai. That is the only acceptable solution in the region rho greater than 0, because the only other possible solution there would involve an admixture of bi, because any solution in this region can be written as a linear combination of ai and bi. The one unique solution, up to some overall constant multiple factor, is ai. So if we take that, we now say, now how, knowing that that is the solution, how do we satisfy the boundary condition that psi of x equals 0 is equal to 0? Well, we're writing the wave function in terms of an Airy function, so we have an additional parameter available to us, which is the a constant offset in the solution. And so that means that we basically we take this Airy function and we sort of start pulling it up until the node lies at the surface of the mirror. So I think you can see that what we're going to get is, here's the lowest solution is going to be like that. Then the next lowest solution, oops, the first excited state has a node, one node in the wave function, and so on. So basically, this curve AI shows you a universal set of profiles of the excited states of the bouncing ball, and they're just obtained by displacing the surface of the mirror to each successive node in the solution AI. Now we'll conclude actually really with just a very brief description of what goes on in the quadratic system. We're not going to discuss that in a lot of detail. The most important case of this concerns the harmonic oscillator, which we've solved elsewhere. But there's sometimes things like a harmonic oscillator with impurities in it or disruptions, and so it's nice to have the ability to solve the general second-order equation. And I'll point out that once again, it turns out that the divergent character of solutions is the generic one. So, for example, in this system, because of the quadratic dependence of x, eventually v is greater than e. If you go sufficiently far away, sufficient large values of x, positive or negative, you're in the forbidden region. So because you have propagation, because you have a wave equation in a forbidden region, you always get a divergent solution. But then there are special cases, and these are exactly the eigenvalues of the harmonic oscillator here. You can see this is a harmonic oscillator looking equation. That when n is an integer, you get bound eigenstates. So this just shows the characteristics of this so-called parabolic cylinder function, and we're not going to make practical use of that in this course, but I thought you should see that, again, the quadratic equations, solutions to the Schrodinger equation for a quadratic potential, are part of this systematic family of special functions that's been developed to solve the Schrodinger equations in general. Okay, that concludes this lecture. I'll hope to see you in the next one.